So today I'm going to define K0 of a ring, K1 of a ring, the Whitehead group of a group, and then start talking about the Whitehead torsion of chain complexes with trivial homology, the Whitehead torsion of a chain homotopy equivalence, and then the Whitehead torsion of a homotopy equivalence, and then the Whitehead torsion of a Morse complex with trivial homology. So then we'll talk about Whitehead torsion. And then I'll state, and if I have time, prove the s-cobordism theorem, which, given what we've already done, is quite straightforward. Okay, so A is our ring unit. I consider the set, I guess it's a set, if we do it correctly, of finitely generated projective left A modules. Okay, so one of those would be called P. And these form a semigroup under direct sum. Do I need to tell you what, does anyone need me to tell them what a projective module is? Okay, good. So these form a semigroup under connected sum, and K0 of A is the Grothendieck group of this, of the semigroup of isomorphism classes of finitely generated projectives. So I didn't say P is finitely generated here. Grothendieck group of classes of finitely generated projective modules over A. Okay, so when you form the Grothendieck group, you consider pairs which formally you write as P minus P0 minus P1, and the equivalence is P0 minus P1 and P0 prime minus P1 prime. These are just formal symbols here. If and only if P0 plus P1 prime is isomorphic to P1 plus P0 prime. Or said another way, anytime you have an exact sequence of finitely generated projectives, you set P2 equal to P1 plus P3. Okay. All right. Let me give you a couple of examples. K0 of the integers is isomorphic to the integers by the rank. So any projective module over the integers, finitely generated projective, is free and it has a rank, and that's the only invariant. Maybe a more interesting case is K0 of the C infinity functions on a compact manifold. So M is a compact manifold. So the C infinity functions on M form a ring. So we can take the algebraic K theory, and this is the topological K theory. K theory of vector bundles over M. So here's the idea. You have a finitely generated projective module over this ring. Since it's finitely generated, there is a free module over this ring that maps onto it with some kernel. So this is a free module, finitely generated free module. A finitely generated free module is simply the global sections, C infinity sections, of the trivial bundle M cross Rn over M. So trivial bundle, vector bundle over M. Its sections are the free module. The basis for Rn gives you the basis for the free module over the C infinity functions. Okay. Now, we can localize at any point. So given a projective module, we can define its quotient px, which is just the projective module tensor over the ring with the real numbers, where this is the map, f goes to ring homomorphism, f goes to f of x. And this is p of x. So it's the, if you will, the fiber of p over x. In this case, it's a finitely generated module over the reals, and therefore it's a finite dimensional vector space. So px is a finite dimensional real vector space. Okay. Similarly, we have the kernel. We didn't need this module to be projective to form this construction. This is a finite dimensional real vector space. Same argument. Now, the magic here from the fact that our quotient is projective is that this sequence splits. It's the fundamental property of projectives. You can always split back. And therefore, this free module is isomorphic to the kernel plus p. Localization then tells us that localizing the free module at x we get the sum of the localization of the kernel at x plus the localization of p at x. Okay, that's true at every x. The point now is that both the dimension of both dimension of cur x and dimension of px are, which way does it go? The dimensions can only jump down, so they're upper semi-continuous. The point is that these are both submodules of the free module f. Look at the fiber over x. So here's the free module at x. We have some subspace spanned by the sections that lie, say, in the kernel. Okay, so there's a finite number of sections that generate the kernel, and their values at x span the subspace cur x inside fx. But if so, whatever the dimension is, you can pick out that number of sections that are linearly independent at this point, and therefore linearly independent nearby. So the fibers at all nearby points at y near x have dimension greater than or equal to dimension at x. Because you take these independent sections at x, being independent is an open condition, so those sections will also be independent at any nearby point. So the nearby points might have larger rank, but they can't have smaller rank. But that's true for both of these factors, and the sum of their dimensions is the ambient dimension, which is constant. Therefore, these dimensions are locally constant. So dimension kern x and dimension px are locally constant. So both of them are smoothly varying families of subspaces of a given dimension. So px in this trivial free module is a smoothly varying family of vector subspaces of a fixed dimension, a locally constant dimension. And that means it's a subbundle. Okay, it's a standard argument. So I've identified P with the global sections of a subbundle of a trivial bundle. So to every projective, I can find a vector bundle whose global sections are P. Sum of projective modules, of course, corresponds to global section, corresponds to direct sum of vector bundles. So this identifies the semigroup of projectives, finitely generated projectives, with the semigroup of finite dimensional smooth vector bundles over the manifold. So that's the definition of K-theory. K-theory is a Grothendieck group of that semigroup of vector bundles, and I've now identified the algebraic K-theory of this ring with that with the geometric semigroup. This argument works for continuous sections and ordinary continuous vector bundles over topological spaces. And it works in the algebraic category as well, works for algebraic vector bundles over varieties. Same argument in both cases. Okay. So this lines up algebraic K-theory and various examples of algebraic K-theory with the more geometric theory of vector bundles. All right, so that's your introduction to K0. Let's talk about K1 of a ring. So here we're going to be considering matrices, GLNA. This is the group of n by n invertible matrices over A. So the entries of these square matrices are in A, and they have to be invertible in that there's another matrix that same right multiplication by it. A inverse gives A times A inverse gives the identity. Well, there's an obvious inclusion of GLNA into GLN plus 1A by taking an n by n matrix with entries alpha ij and putting it in like this into GLN plus 1. It's an easy exercise to show that if alpha, this n by n block, is invertible, then the inverse is formed by taking the inverse of alpha in the n by n block and putting a 1 down here. So this map is a inclusion of groups. So you get invertible matrices, and the inverse is just the image. So we can form the limit as we let n grow to infinity of GLNA under these inclusions, and that is GL of A. The infinite general linear group of A So these, you can think of these as matrices, infinite by infinite matrices, which in fact have an upper left-hand block, and outside of that look like the identity. So they agree with the identity outside of some upper n by n block for some n. And again, inverse is, these matrices multiply in the obvious way, and inverse is given by taking the inverse of this thing and extending to be identity and all the other components. So this is a nice ring. And now we form GLA divided by the normal subgroup generated by elementary matrices. Where an elementary matrix is a matrix of the form the identity plus alpha EIJ. So alpha is an element in the ring, and EIJ is the matrix with a 1 in the IJ's place and 0 elsewhere. So these are the matrices that agree with the identity except for one entry alpha, and everything else is 0. And the position of alpha is IJ here. I is not equal to J. Okay. So there's one off diagonal entry. All the diagonal entries are 1. There's one off diagonal entry, and it can be an arbitrary element in A time in that spot. So this is the analog of adding a multiple, the multiple being alpha, which is an element in A now, of one column to replacing one column by its sum of it plus alpha times another column. It's the analog of that. So you take the normal subgroup generated by these elementary matrices. That's a normal subgroup. You take the quotient of GL by that normal subgroup, and that is K1 of A. And it turns out that this normal subgroup is the commutator subgroup. So K1 of A is the abelianization of GL of A. I'm not going to prove that, but it's not too difficult. So K1 of A is an abelian group. It's the abelian quotient of the general linear group. But for our purposes, it's more important to know that it's the normal subgroup generated by these elementary matrices. Okay. Now, the special case, when A is the integral group ring of a group. So here G is a group. We can form the integral group ring. Remember, this is just finite linear combinations of integer multiples of group elements. Formal finite linear combinations, you add coordinate-wise in the G's. That's the integral group ring. It's a group under the, it's a abelian group just by adding the integers entry by entry, and it's a ring because you can multiply the group elements and the coefficients, so you can multiply these sums together. Makes a nice ring. And the Whitehead group of G is by definition K1 of this ring divided out by plus minus G, where G is in G. So what we're doing is we're taking K1 of G, this general linear group, infinite general linear group, mod the elementary matrices, and we're also dividing out by the image of GL1. Well, actually, I don't think that's right. the elements plus and minus G are 1 by 1 invertible matrices. The inverse of plus minus G is plus minus G inverse. So these are invertible 1 by 1 matrices. I don't actually know. It seems to me like there are other units in general in G of Z beside these. Does anybody know? Dave, do you know? There are other units in Z of G? Seems like there should be, but I don't actually know. Anyway, whether or not there are other units, these are elementary units. So plus minus G is an elementary unit. In Z of G, and we divide out by those. Okay, so that's the Whitehead group. Now this is related to what I've been talking about before with handle slides, in that the three operations we're allowing are column operations. In defining K1, we allowed ourselves to divide out by adding a multiple of one column to another one. Here we're now allowing ourselves to multiply a basis element by a group element, or change by plus or minus a group element. So change the sign, multiply by a group element, or do the elementary column operation of adding a multiple of one column to another. So those are exactly the moves we considered before when we were working over the integers. Now we're working over the ring ZG, the integral group ring of G. Okay. All right. So now, suppose you have two lattices, L and L prime are lattices over the integral group ring of G. That is to say, finitely generated free modules, and we have bases with bases. Fixed, okay? And we have an isomorphism alpha from L to L prime. The Z of G map, so a map of Z of G modules, which is an isomorphism of Z of G modules, the same thing as an isomorphism of the underlying abelian groups. We take the matrix for alpha in this basis, and that's an element in GL in ZG, and its image in the Whitehead group of G, which is a quotient of this by the elementary matrices and plus minus G, is called the Whitehead torsion of the isomorphism alpha.
So to answer
So
your
elements
previous
in the general linear group have Whitehead torsions, their image in the Whitehead group. And so an isomorphism between lattices with Z of G basis becomes a matrix and therefore has a Whitehead torsion. This Whitehead torsion, of course, depends on what bases you have for L and L prime. For example, if you have a basis for L and you push it forward by alpha to get a basis for L prime, then the matrix for alpha with respect to those two bases is the identity. Whitehead torsion is, Whitehead torsion will be 0. So it depends on what bases I have for L and L prime, but I am allowed to do operations on these bases which will not change the Whitehead torsion of the map. I can reorder the bases. I can add a multiple of one basis to another, and I can change the bases by sign and multiplication by a group element. Those operations will change the matrix, but will not change the Whitehead torsion. But a more general automorphism, change of basis, will of course change the white-edge torsion arbitrarily. Okay, that's all I want to say on that page.
To answer your previous question, it seems that the characterizing the units is hard enough to warrant a paper per group. I'm finding
okay, not surprising. Thanks, Dave. So these are the elementary units we're talking about, not arbitrary units. Okay, so that's the Whitehead torsion of an isomorphism. We can generalize this to the Whitehead torsion of a chain complex whose homology is trivial. So now let C star be a finitely generated free ZG chain complex. So always when I talk about and suppose we have bases. We have bases given for the chain groups, the CK. And suppose the homology of this chain complex is trivial. So a special case of that is, suppose you have two lattices, two free Z of G modules, and an isomorphism between them. You let this be the chain group in degree K, and this the chain group in degree K-1, and this the boundary map. That would be a chain complex with trivial homology. So more generally, I have a chain complex with trivial homology. It has a Whitehead torsion Whitehead of C in the Whitehead group, which I'm going to define now. Okay, so we have the boundary map, C star to C star minus 1. Since C is free and the homology is trivial, there exists a chain homotopy that's a map H from C to C star plus 1 that connects the identity to 0, meaning boundary H plus H boundary is the identity minus 0, which is the identity, of course. Okay, so this is an easy exercise of use the freeness of the domain and the fact that the freeness, so you're looking for a map from C star to C star. Use the fact that this one is free, so you only make a construction on the basis elements, and for each basis element you look at the equation you have to satisfy, and it turns out that you have an element in the dimension of the basis element that is the cycle. Because the homology is trivial, it is the boundary of something. You just choose the something that it's the boundary of to define the chain homotopy. It's a standard argument. I don't think I'll go through that. Okay. Now, let's look at boundary plus H, which is a map of C even to C odd. That's how I'm going to think of it. So boundary lowers degree by 1, sends even degree things to odd degree things. H raises degree by 1, so it sends even degree things to odd degree things. So I have a map here, and the claim is that it's an isomorphism. And the proof is very elementary. Let's compose it with itself. So boundary plus H also gives a map back. So the same symbols also refer to a map back from C odd to C even. So let's take the map from even to odd and compose it with the map from odd to even. So this is a map from, let's say, C even to C even. And what is it? Well, it's boundary squared plus boundary h plus h boundary plus h squared. Well, boundary squared is 0. Boundary is boundary. Boundary h plus h boundary is the identity. So it's identity plus h squared. Well, so I haven't quite found an inverse for boundary plus h, but I found something that I can follow it by, so that the composition is the identity plus a nilpotent element. So then, so h squared is raising degree by 2, and thus it has an inverse, just the formal power series, which terminates at h plus or minus h2n. Just by degree considerations, this is a finitely generated complex, so it has only finitely many non-trivial groups. Therefore, the composition of this with this map coming back is invertible, or in other words, multiply on this side, I guess, by this truncated power series, which is the inverse of this thing, and that composition will be the identity. So this implies boundary plus h is an isomorphism. And so we define the Whitehead torsion of the chain complex to be the Whitehead torsion of this isomorphism. I should say, by the way, the bases for the various chain groups give us a basis for C even and a basis for C odd. You have to decide how to order them, but that doesn't really matter. And therefore you have chosen bases for these two groups. So this isomorphism has a Whitehead torsion. It's an easy exercise that I won't go through, that this Whitehead torsion of boundary plus h is independent of the choice of h. Okay, so you get a well-defined Whitehead torsion, the Whitehead torsion of this chain complex with basis with trivial homology. And of course, as before, if you change the basis arbitrarily, you will change the Whitehead torsion to any other element. But if you only allow elementary transformations, you do not, on the basis, you do not affect the Whitehead torsion. Elementary chain, bases change, basis change, changes leave the Whitehead torsion of C star unchanged. But a general change of basis will vary it arbitrarily. Okay. Now let me give you a little proposition that says that the Whitehead torsion of chain complexes is really just a disguised version of the Whitehead torsion of an isomorphism. So C star is a free, finitely generated ZG chain complex. Over the integral group ring. Okay. So we're going to do two operations to this chain complex. So after stabilizing by adding complexes of the form boundary from di plus 1 to di, these are finally generated free CG modules with bases, and boundary is the, if you will, identity with respect to these bases. So it's an isomorphism, but it carries the basis for di plus 1 to the basis for di. So you're allowed to add these sorts of trivial chain complexes of length 2 where the bases are matched by the boundary map. You're allowed to do that in various dimensions. So you stabilize, you add a bunch of those. And then after elementary change of bases on this bigger chain complex, the one that you've gotten by taking C and adding these trivial pieces to it, the following hold. Okay. Each CI, so CI now refers to the original chain complex augmented by these stability pieces, these extra Ds. I don't want to change notation. You can write CI as AI plus BI, where AI and BI are free, and the basis for CI is the basis for AI followed by the basis for BI. So in other words, AI and BI are given by disjoint subsets of basis elements for C. Some of the basis elements for C are basis for A, and some are bases for complementary set is basis for B. The boundary map from CI plus 1 to CI is of the form AI plus 1 project on to BI plus 1, map by some map HI plus 1, which is an isomorphism, onto AI, and then include AI into CI. Okay. So we've broken each CI up into a sum of pieces, and the boundary map, no, I guess it goes the other way, the way I've done it. The boundary map goes from the second piece isomorphically to the first piece. The next boundary map goes like that. The previous boundary map comes down like that. Okay. So we've split the chain groups into sum of free pieces, the chain modules into a sum of free pieces. The boundary map is simply the first piece goes to 0, the second piece maps isomorphically onto the next lower first piece. Fix, I should have done this earlier, fix K, an integer, will be in the range where C star is non-trivial. Okay. And for all I not equal K, HI plus 1 mapping BI plus 1 to AI matches the bases. And then HK plus 1 mapping BK plus 1 into AK is an isomorphism. So I've made this chain complex look completely trivial in all degrees except K. So here's my picture of the chain complex. These are the A's, these are the B's, here are the boundary maps. These are really the identity in the sense that the basis here goes to the basis here. Here's the one where you just have an isomorphism, and here, again, you're back to the identity. So all these maps match the B with the next lower A by a map matching the basis elements, except for one. So here's BK plus 1 and AK, where you just have an isomorphism. Well, in this case, the weighted torsion of the chain complex is the weighted torsion of this remaining HK plus 1 of that isomorphism. Not surprising, the weighted torsion of everything else has got to be trivial. You're just left with this one non-trivial isomorphism, and its Whitehead torsion is the weighted torsion of C. As a corollary, If the weighted torsion of C star equals 0, then we arrange that BI plus 1 to AI matches bases for all I. Since the weighted torsion of this map is the weighted torsion of the chain complex, all the others already match bases. If the weighted torsion of the chain complex is 0, I can make elementary change of basis over here until this isomorphism also matches bases. Okay. All right. So that's a way to think about the weighted torsion of a chain complex. You can if the homology of the chain complex is 0 and everything is free, after stabilizing a little bit, you can concentrate everything in 1 degree. Everything else is completely trivial. Okay, so this is what we've been talking about, is the homology of the free chain complex with the Whitehead torsion of a free chain complex with trivial homology. Now I can use that to define the Whitehead torsion of a chain equivalence between free chain complexes with bases. So now we have 2 chain complexes, C and C prime. These are free, finitely generated ZG complexes with bases. Anytime you're talking about torsion, you have to have bases given somehow. And phi mapping C into C prime induces, it's a chain map, induces an isomorphism on homology. So it's a chain homotopy equivalence. We define the Whitehead the Whitehead torsion of phi okay. And the way we do it is associated to a chain map, there's a mapping cylinder. It's a new chain complex. In degree n, it is, let's see, how does it go? Bn, An to Bn. Yeah, it's the sum of Bn and An minus 1. And the map, the boundary map from the chain complex in degree n to the chain complex in degree n minus 1 is given by the matrix boundary B minus boundary A, phi 0. Let's see if that works. So if you have an element B of degree n and A of degree n minus 1, when you apply this thing, you get boundary of Bn plus phi of A n minus 1. That's an element in degree n minus 1 in B. And the second thing you get is minus boundary A n minus 1, which is an element in degree n minus 2 of A. So exactly works. It's an easy exercise. The fact that phi is a chain map, and that's what accounts for this minus sign here, means that boundary squared is 0. So this is a chain complex. And we have an exact sequence. I'm sorry, I switched notation, didn't I? Excuse me. This is A star to B star. I switched notation in midstream. So I have 2 chain complexes with bases, A star and B star, a chain map between them, which induces an isomorphism and homology. I form the mapping cylinder. I now have an exact sequence of chain complexes. shifted. I never know which way to shift. Okay. So the inclusion of B into A preserves degree, and it's the obvious inclusion of B into A. And the first column of this matrix is boundary B0, which says this is a chain map. So this is the inclusion. This is the projection, and it shifts degree by 1. So if you have an element in degree n in the mapping cylinder, and when you take its projection to A, you get something in degree A minus 1. And that's what this shift by 1 means. But it, again, commutes with the boundary map up to a sign, which is imposed by this minus 1. Okay. This is a short exact sequence of chain complexes. It leads to a long exact sequence of homology, which looks like Hn of B into Hn of the mapping cylinder into Hn minus 1 of A into Hn minus 1 of B, and so on. But these are, this is the map phi star. These are isomorphisms. So by the 5 lemma, the homology of the mapping cylinder is 0. So the mapping cylinder is a free, finitely generated Z of G chain complex, being the chain groups being the sum of 2 such objects, and its homology is trivial, and it has, the chain groups have a basis, namely the chain group in degree n in the mapping cylinder is a sum of Bn and An minus 1. So you have the given basis for Bn, the given basis for An minus 1. You concatenate them, you get a basis for the mapping cylinder. So with bases, given bases, homology is 0. So we have the Whitehead torsion of this chain complex, and that is the definition. Of the Whitehead torsion of this chain homotopy equivalence. If you change the bases of A and B by elementary transformations, you will not change the Whitehead torsion. If you make arbitrary basis changes, you will move the Whitehead torsion arbitrarily. Okay. Maybe just one lemma that I won't prove, but just to give you a sense of how this works. Suppose you have 3 chain complexes. And chain maps, and suppose phi and psi induce isomorphisms on homology. These are free, finitely generated Z of G chain complexes with bases. Then the Whitehead torsion of phi plus the Whitehead torsion of psi is the Whitehead torsion of psi composed phi. These are chain maps inducing isomorphisms and homology. Same, this is not a short exact sequence. This is just a diagram of chain complexes. Have an isomorphism in chain complexes, homology isomorphism here, homology isomorphism here. I can take the composite, which is a homology isomorphism there. So I have 3 Whitehead torsions, and they obey that relationship. Okay. All right. Now we want to turn from chain complexes to geometry. So X is going to be a finite, it's going to be a finite CW complex, and we fix a base point Not important, but let's take it to be a 0 cell. I want to define a chain complex associated with X and coefficients Z pi 1 of X. Okay. So this is going to be one of these chain complexes of the type we've been talking about. It will be finally generated, free finally generated over Z pi 1 of X. It won't have a trivial homology in general, but at least it'll be a chain complex of the type we've been considering. Free finally generated chain groups over this ring. Okay. So in order to do this, for each cell C in X, I must choose an orientation for C. This is C, doesn't look like C. An orientation for C and to a path from the base point to the central point of C. Okay, so here's my base point X naught, which is a 0 cell. Here's some cell in the CW complex out here. Here's its central point. This is cell C, and let's say the central point is EC. I need a path, I'll call it omega of C, from X naught to the central point of the cell. So that's what I got to choose. Now, you might worry, and once I make those choices, I'm going to have bases for my chain complex over Z pi 1 of X. You might worry that, well, I can change the orientation. Well, that's going to affect things by sign. You might vary this path, but that will only change something by an element in the fundamental group. So I'm going to have a basis well-defined up to plus or minus G in pi 1 of X when I finish. All right. So given those choices, CK of X is by definition the free Z pi 1 of X module generated by the cells of dimension K. Okay. Now I need to define the boundary map. So let C be a K cell and let B be a K minus 1 cell. So this is a generator in degree K, and this, well, I have to define, so this is a generator in degree K. I have to define the boundary map of this generator in degree K, and it's supposed to be an element in CK minus 1 of X. So it's supposed to be a linear combination, alpha J B J, where these are cells of degree K minus 1, and these are elements in Z pi 1 of X. Okay. So I need a linear combination of the symbols associated with the cells in degree K minus 1 with coefficients in the integral group ring of the fundamental group. So I'm going to tell you what the coefficient, so what is the coefficient of BJ in boundary CK? I can tell you that for each bj, then you'll know what the sum is. Okay. Well, we do the sort of thing we always do. We look at the boundary, look at the attaching map from the boundary of the K disk into the K-1 skeleton. So this is alpha of C is the attaching map. For C. Okay. So this is a cell. It's formed by attaching, it's formed by taking a disk of degree K, of dimension K, and attaching its boundary to the previous skeleton. Well, I might as well assume, as you usually do when you're calculating homology, that alpha C is transverse to midpoints, the central points of the, well, to the central point of BJ. So if I had a two sphere as my head, so here's a 3-ball, the 2 sphere is being attached, and here's BJ, which is a 2 handle. I take its central point, I arrange that the attaching map, alpha C, is transverse to this point. So the preimage of alpha C, so the preimage under alpha C of the central point for BJ will be a disjoint union Y1 up to YR, a finite set of points. Each YI has a sign, which is all you usually think about when you're not worrying about the fundamental group. The sign tells you about the degree of the map at this point using the orientation of the boundary from the orientation of the disk and the orientation of BJ. So the sign depends on the orientations. There's also a group element associated to YI. So an element in the fundamental group. So here's X. Here's the cell C, and we have some path to its central point. Now we have the lower cell BJ and its central point. We have it, so this is omega C, this is omega BJ. So I have those two paths, they're given to me. Now I have in the boundary this YI, so I just take a path in the cell C from its central point to YI, and then I take, well, and that YI is identified with BJ, so if you do omega C YI, call this lambda I, the path in the cell I'll call lambda I. And then I do omega BJ inverse. This is a loop based at X. Starts at X, goes up, down the cell, goes up to the central point of the cell by these paths that I chose a while ago, moves in the cell down to this point YI. YI is identified with the central point of BJ, so I take the inverse of the path associated to BJ back, and that gives me the loop. Okay. So for each point of intersection, so for each YI in the preimage of the central point of BJ, I get a sign, epsilon YI, which is plus minus 1, and I get G of YI in the fundamental group. And now I sum over I the signs times GYI. Well, that's a linear combination of elements in the fundamental group with integer coefficients. So that's in the integral group rate. And that's the coefficient. So let's call this alpha alpha j. Depends, it goes with bj, and then the boundary of the class of C in degree k is the sum over the k-1 cells of this coefficient times the class of bj and k-1. Okay. So that defines a boundary map from ck of x with these coefficients into ck-1. Maybe it's not clear from this description that boundary squared equals 0, though the usual argument can be modified slightly to see that that's true. But let me give you another way to think of this construction where it'll be obvious that boundary squared is 0. So another construction of this chain complex. I'm gonna do it on the time. Whoa, okay. Thus pass to the universal cover x tilde, and it has an induced cell structure. We choose a lift x tilde naught of our x tilde of our base point x, so that we're going to use that as base point. Okay, now for each cell C of x, we choose a lift C tilde of C, being one of the cells in x tilde, and it's determined for us by the path. It is the lift such that the lift of omega C starting at this particular lift of the base point ends at the central point of C tilde. In other words, it's equivalent to choose these paths omega C, paths from the cell out to, from the base point out to the cell. That's the same thing as saying which lift in the universal cover of C you want to use. You lift this path starting at the chosen base point upstairs. You see where it ends. It ends at the midpoint of one of the lifts of C, and that's the lift of C you use. Okay, so what these paths are doing for us is they're giving us choices of the lift of our various cells up in the universal cover. So up in the universal cover, we have the set of cells lifting C are parameterized affinely by the fundamental group, and we're choosing one of them. We could have chosen any one. Different choice of paths would give us different choices of C tilde. So the C tilde with the induced orientations coming from the orientations we chose of C give a basis over Z pi 1 of x for the chain group in degree k of the universal cover with ordinary integer coefficients. So as I said, the fundamental group acts here. It acts freely on the set of lifts of C. If we choose one of them, then we identify all the lifts with a copy of the integral group ring, and we do that for each cell of degree K downstairs. So this homology of the universal cover with its natural z pi 1 action given by the covering transformations becomes a free module, and these are its basis elements. These oriented cells give us the basis. And my construction of the boundary map, so we now have the ordinary boundary map for C star X tilde coefficients in Z. And of course, boundary squared is 0 because this is the usual boundary map. But the ordinary boundary map and the universal cover is identified with this Z pi 1 of X boundary map that are defined downstairs. So in fact, the chain complex of X with coefficients Z pi 1 of X is identified with the chain complex of X tilde with integer coefficients once we choose the paths omega of C, or equivalently the lifts C tilde of C. Well, and boundary squared is 0 over here for the usual reason, so boundary squared is 0 there. So that's my definition of the chain complex, and I see I'm pretty much out of time. Well, I guess I have time to say this. So now suppose X and Y are finite cell complexes, and F mapping X to Y is a cellular map inducing an isomorphism pi 1 of X to pi 1 of Y f of X. Okay. Then we get an induced map F star from the chains on X with coefficients Z pi 1 of X to the chains on Y, same coefficients, Z pi 1 of X. I mean, it's really pi 1 of Y f of X, but that's identified with pi 1 of X. Okay, so these are free finitely generated chain complexes, and this is a cellular map. If F star induces an isomorphism on homology of these chain complexes, then we have the Whitehead torsion of F star. Okay. Now, to say that F induces an isomorphism on the fundamental group and F induces an isomorphism on the homology of the universal cover, so F mapping X to Y is a homotopy equivalence if and only if, say for path connected spaces, if F star from pi 1X to pi 1Y is an isomorphism, and F star in the homology of the universal cover is an isomorphism. So these conditions, the map induces an isomorphism on the fundamental group and on these chain complexes with coefficients in the integral group ring of the fundamental group, are the same as the condition that F be a homotopy equivalence. So we now have the Whitehead torsion of F star if F is a cellular map, homotopy equivalence between finite CW complexes. But in fact, if F and G are such, and they are homotopic, then there is a cellular homotopy, cellular approximation again, between them, H mapping X cross I with an obvious cell structure into Y, between them, X cross 0 into X cross I, and X cross 1 into X cross I have trivial Whitehead torsion, sort of obvious to see. That means that the Whitehead torsion of F star equals the Whitehead torsion of H star equals the Whitehead torsion of G star. So if you have cellular maps, which are homotopy equivalences between finite cell complexes, which are homotopy equivalences and which are homotopic, then they have the same Whitehead torsion. But every map, every continuous map from X to Y is homotopic to a cellular map. We define the Whitehead, if F is a homotopy equivalence, we define the Whitehead torsion of F to be the Whitehead torsion of any F prime, where F prime is cellular and homotopic to F. By this argument up here, this gives a well-defined notion of the Whitehead torsion of a homotopy equivalence between finite CW complexes. So the point is that the basis that we need for the chain complexes, the algebraic basis, comes from the geometric structure of the cells. So if you have a cell complex, that cell structure determines the basis that you need in order to start defining Whitehead torsion. So a homotopy equivalence between finite cell complexes has a well-defined Whitehead torsion. A homotopy equivalence between finite simplicial complexes has a well-defined Whitehead torsion. And we'll use that next time when we start talking about the s-cobordism theorem. So I guess all I got to do today was give you the basic introductions to K-theory and the Whitehead torsion. We'll talk about the Morse complex and its basis related to the bases we're talking about here for cell complexes, and then state and prove the s-cobordism theorem next time. Questions? So as I said, this was a more algebraic or formal lecture than these heavy geometric constructions we were doing last time. And it will be pretty much the same on Wednesday when I prove the s-cobordism theorem. All right, no questions?
Maybe
Yep.
I can like a general question. So is there a reason why this is called a torsion?
I'm sorry, is there a reason why?
This is called torsion. Like,
Yeah, I'm sorry, I'm not,
torsion in what sense?
I can't understand what you're asking. Sorry, try again.
I'm trying to ask, is there a reason why this is called a torsion?
Oh, why it's called torsion. I think, I don't actually know the answer to that. I think the idea is if you can line up the geometric pieces so that they match in a reasonable way, then this invariant will vanish. But if your chain complexes are twisted, or your map is twisting the chain complexes around somehow, so that you can't match the bases up, that's some form of twisting or torsion. But I don't know. I don't actually know the root of the word or why it was chosen.
Okay, thanks.
Anybody else? All right. S-cobordism theorem on Wednesday. So long all.